So this is a continuation of the bin packing problem and solving it using Python and Gurobi. In the previous episode, I showed you how to create a mathematical model for the bin packing problem. This is, of course, one variant of the mathematical problem that can be created for the bin packing. There's actually at least two different, significantly different ways of solving this problem, modeling this problem mathematically. So here the model is, we have xij variables that say if item I is assigned to bin j, and yj variables that say bin is used. And this is the full model. And if you recall, we have actually 9 problem instances. So 9 different instances of the bin packing problem. We're going to just focus on the first of them for now. The first one has capacity C. The weights are here. And then we did also calculate the lower bound, which is a fractional lower bound. So actually, if you look at this model, and if you were to change xij, rather than have it from 0 to, 0 or 1, if you were to change them, and also y, to be between 0 and 1, including allowing fractional values, then actually this model would find exactly the solution with a value sum of w divided by c, right? Because we would be allowed to pack a part of an item I into bin j, and therefore you would actually end up using all capacity in all bins completely. There wouldn't be a problem, right? And then the total number of bins used would be exactly sum of w divided by c, right? So if you do what we call a linear relaxation of this model, fractional relaxation, then this model will give you a solution value that is equal to the sum of weights divided by c, and it would be fractional. Now, because we know the number of bins used must be integer, so we actually rounded it here, and we took this as an integer value, right? So we're going to focus on this first instance, 60 items, capacity 150, smallest weight is 23, largest weight is 98, and we know actually lower bound by our simple formula here is 22, right? And maximum number of bins is 60, assuming that every item is packed in a separate bin. That's an easy, very trivial solution. I'm sure we will be able to do much better than this. So here we have the initial code that just extracts this first instance, this instance number 0, from the list of set of instances. And then it just takes its name, its capacity, and w are now extracted into c and w. N is calculated, lower bound using our function upper bound, and this is what is printed here, so we know what instance we're solving. And I've already created the model. Remember, earlier we imported Gurobi Pi into the main namespace. So now we can use the model from Gurobi. And I also set the parameters log to console and time limit. This is actually the default value, but we may later change it. So now that we have created the model, we need to create the decision variables. So as we said, we have xij variables, which I ranges from 0 to n minus 1, and j up to ub minus 1. So to do that, we need to say x equals model add vars, and we need to say, if we give it n and ub, then we mean the variables x will be indexed by first index in range n and the second index in range ub. Actually, this is going to work the same as if we were to say range n and range ub, right? But I'm not going to leave it like this. This is actually equivalent, right? So we define these variables, and we also want to say v type, variable type, grb binary. Okay, so that indicates the variables are binary. I'm going to run this just to see that it doesn't, that it actually compiles. Similarly, the y variable, but y variables also binary, but they will be only indexed by j, that ranges from 0 to ub minus 1. So I leave this here. They are also binary. I have x and y variables. Now I need to set the objective. So I'll do model set objective. And the objective is the summation of yj. So I will use quick sum. If you remember, this is the function that is a faster version of the Python sum that is created by Gurobi for creating formulas. So quick sum will be adding yj for j in range ub. Right? And we also need to specify that this is a minimized function. Again, let's compile this. It seems it's working. So Control Enter is a nice way to compile it, or you can press this Run selected cell. Then we need to add constraints, and if you recall, we had different types of constraints. We had two types of large constraints. So we said for every item I, let's have the summation of xij variables equal to 1. So there are many ways of adding these constraints. And I'm going to write first, for each item I in range n, we need to ensure item I is packed in exactly one bin. So we need to say model add constraint, and we want to say quick sum of xij, right? Similarly to the above quick sum here, we will say quick sum for, but that's right, for every bin j in range ub. So what this sum does, it just takes all xij variables with a fixed I and changing j in this range, right? And this sum now should be equal to 1 if we want to pack every item in exactly one bin. I compiled it, this works. This is one way of putting this. An even more condensed way is to say, well, this is like adding multiple constraints. So I could have added it this way. I could say add multiple constraints. You have to add the letter S here. This is important. And then say this constraint repeated for every I in range n. So this is a generating function. You can find help about this in Gurobi documentation. Gurobi documentation, if you recall, it can be found in gurobi.com/documentation. And right, and you can find help about all kinds of parameters, reference manual, and API details. And you can find, for example, add constraints. And add constraints will give you help on how to generate, right? How to create generators like multiple constraints. This is one constraint. This is multiple constraints. How to create multiple constraints of the same structure at the same time. Okay, so this is actually an equivalent of this. So I can use either of those. Actually, there is even more complex ways of generating this constraint, because we can say, well, this sum, we can actually calculate it incrementally. So let's call it some expression, and you could say expression equals I believe there is a linear expression in Gurobi, and we could say for each j in range ub, we want expression to be incremented by xij. And so what that means is this. Create a constraint for every I. For every I, start with an empty expression. This expression just has a 0 value, right? Just 0 here. And then go for all bins, j, and then for each of those j's, take variable xij and add it to the expression. So we're just building this sum incrementally, right? And then at the end, we say model add a constraint. The expression must be equal to 1, but this expression is actually now containing the sum, the appropriate sum of some of those xij variables. Why am I showing you this? Because this is sometimes useful when you have complex conditions on what you should add to the expressions, or if you want to build multiple constraints at the same time, you could have a list of expressions and just take this variable, check some conditions, add it to the right expressions and not add it to others, and then add the constraints. But obviously, this is, again, another equivalent way of building this constraint, which is here defined in one line. So I'm going to just leave this, add constraints, quick sum, xij for j in range ub equal 1, and then, right, so this constraint, we could also put comments. Objective is minimize the number of bins used. This is the constraint, each item in exactly one bin. We also need the constraint, the last big constraint, which is saying for every bin, make sure what you pack in it is no more than cap C, which is the capacity, and obviously only if the bin is actually used. So only if y is 1, if y is 0, then the capacity really is reduced to 0, right? So we could say, maybe I'm going to copy this comment, total weight in each bin is limited, right? So my comment here will be limit total weight in each bin, also link xij with yj. So how do I add this constraint? Again, it's add constraints, right? I will write something here, and this something will have to be repeated for each j, for each bin in range ub, right? Now what was this constraint? It is a quick sum, right? X weight of item I times xij, right? This is the rate, and this I have to do this for all items. So for a fixed bin j, I have to check all items I, and I have to add their weights, right, multiplied by the binary indicators saying if they are in this bin or not. And then this quick sum has to be less than or equal C. Well, it would be C if the bin is used for sure, but it's C times yj, where yj indicates if the bin is used, right? And as you remember, we said this is what tells us if the bin is, the capacity has to be limited, and also the capacity is there only if the bin is actually used, right? Now, because the domain, so if you look at our model, right, we define the variables, we define the objective, we define these two big constraints, and the domains have already been defined when we were defining the decision variables. We see that the binary variables are actually binary through these two lines. So this should work, and all I need to do now is try to do model optimize to see if my model is working. So let's try and run this, and let's see. And what I want you to see now, this model ran for like a second and a half, and it found a solution with 22 bins. So if you recall, our lower bound was actually a strong lower bound at 22. We could find a solution with 22. Let's try to solve instance number 1. Right? It also has 60 items. Lower bound is 20. And notice this instance is actually solving. Now it's 5 seconds of solving. A solution found is 21, and the best bound is 20, and it is still solving. And it cannot find a solution with 20 bins. And we really don't know. Maybe the optimal solution is 21, because we already have a feasible solution with 21 bins. But maybe it is 20, because the lower bound, right, we know it's not better than 20, but we don't know. Maybe 20 is still possible, because that's what the lower bound tells us, and even within the solver, that's what it is determining. So what I want you to see is that this solver now it's exploring the branch and bound tree. I have a separate video on how the branch and bound method works, which I recommend you use on my channel, Decision Making 101. But right here you see that as the branch and bound method works, it starts from some kind of solution. At the beginning, it was 39 bins. It quickly actually managed to improve it down to 21. And then it couldn't improve it further, and it started checking the tree, dividing the tree, and this shows you how many nodes of the tree were created. So actually quite a lot of nodes. And this shows you how many are still unexplored at this. After 60 seconds, there was still 650 nodes of the decision tree, of the branch and bound tree, unexplored. And it shows you the best that the solver is still hoping to find is a solution with 20 bins, but it couldn't find anything better than 21 so far. It also shows you something called cutting planes. The solver added a lot of additional constraints that were expected to help it solve this problem, but still it couldn't find a solution, and it tells you time limit reached, and actually that's why I set it to 60 seconds so that we don't wait forever. And it shows you the best solution, 21 bins, the lower bound is 20, and the gap, which is the percentage difference between those two, is almost 5%, right? We can try another. Actually, let me reduce just the time limit to, let's say, something like 30 seconds. And let's try, actually, I shouldn't have run this. This is in 30 seconds. So let me run this now for the third instance, or instance number index 2. This one has now 120 items. Lower bound is 48, upper bound 120. And again, you can see how the solution is progressing. Right? It started with 86 and it went down quickly to 49. And notice lower bound is 48. And here the solver is actually showing a fractional bound, but it does know that this solution must have an integer value. So even though it is displaying 47.18, at the end it's going to tell us it's 48 minimum. And again, the solver has a problem. See, 48 is the bound, 49 is the best solution. And I couldn't find the exact best solution. And we can try, let me actually jump to something like instance number 4 and try to solve it again. And you see, the larger the instance, the more problems the solver has, and the longer takes. Right? Again, this is one. So this problem often has this, that it's easy to pack in a number of bins, but the lower bound often shows that it's one bin less that could possibly be achieved, and until the problem is solved to optimality, we don't know. So let's solve one more instance. Let's solve instance number 5. This instance already has 500 items, and you will see that even the problem is quite large now, has quite a lot of variables. You see it starts with solution with 346 bins, goes down to 250, 227, 203, but it's still quite a few bins above the best bound. And right, and then after 30 seconds, we are able to find something with 203 bins, and the lower bound is 198. So maybe there is a possibility to improve 5 bins by 5 bins, right? So I will stop this episode at this point, and the next episode, I'm going to try and implement a heuristic. But before I do that, I will actually try to decompose this. And I'll try to say, try to put this as a function, define model bin packing, and get the parameter CW, and then log to console, and time limit, let's say equals 30, the default value. And then I'm going to indent this. And also, what I would like to do is perhaps return the model objective value and model best bound, which is objective bound, right? So if we do this, so what does this return? This returns the best integer solution value. So in this case, it would return 203, and objective bound will return this value 198, which is the best possible objective value that perhaps the model could still find. So what I will try now is say, right, if we can actually reorder this, we can say now we can say, take this instance and call the model for it, model BPP for this instance with no time limit, and then just print what we get, and we could even, we can print the result. Right, so this is now solving for 30 seconds, and after 30 seconds we get this solution where this is the best of solution value and this is the best bound. And the question is now, can we improve this? Notice that in this example the solver didn't even start exploring the branch and bound tree, so the number of explored nodes is 0. It was still at the initial node. It was just adding the cutting planes and running some heuristics, and this is the best it could find. It could find a solution with 203 bins, but perhaps it can improve it by up to 5 bins.